Okay, so we're going to talk about a method for finding the inverse of a matrix. We gave a formula previously for a inverse of a 2 by 2 matrix, and we want to up that to matrices for 3 by 3 or larger square matrices. In order to do that, though, we've got to do some important preliminary work, and we're going to talk about, first of all, elementary matrices. They play an important role in what we're going to talk about, and actually we're going to look at a very important theorem concerning matrices that are invertible. And then in the midst of that process, we will find this method or algorithm for finding the inverse of a matrix. So let's start off with the definition of an elementary matrix. These are square matrices. They're obtained by performing one row operation, just one, on the identity matrix. So if we perform one row operation on an identity matrix, then we get an elementary matrix. So remember, the identity matrix, what that is a matrix with ones down the main diagonal and zeros everywhere else. So for instance, the 3 by 3 identity matrix would be this matrix here. And of course, when we're talking about matrices that are invertible, which we'll get to again here in a minute more in detail, this is the inverse notation for a matrix A. If I multiply any matrix by its inverse, we get the identity matrix, right? That's the idea. That's part of that's the definition, really, of an inverse and an invertible matrix. Now, look at these elementary matrices. I'm giving them, denoting them capital E for elementary matrix with subscripts to denote the different ones. How was this one obtained from the identity matrix? What row operation was done? Well, clearly, row 2 was multiplied by 3. We did that row operation where we multiply a row by a non-zero constant, right? And we obtain this matrix, so this matrix is elementary. How did this matrix come about from the identity matrix? Now, if you think about it, we interchanged what? Rows rows 2 and 3. Row 1 is the same as the original. Rows 2 and 3 were interchanged. Okay. And then what about this one? How did we get this from the identity matrix in one row operation? Well, the way we did it was we added a multiple of one row to another. We added 2 times row 3 to row 1. So this one was 3 times row 2, right? Replacing row 2 with that result. This was swapping rows 2 and rows 3. And this was taking row 1 and adding 2 times row 3 to it. Okay, so those are all illustrations of how we can get an elementary matrix. So it's only one row operation, not more than one. Now, something interesting happens. Let me take a look at these individual elementary matrices and see what happens when I multiply a matrix on the left by an elementary matrix. So here's a matrix A, and it's obviously contrived to in a certain order, but I want you to see the pattern very easily. What happens when I multiply E1 times A, which I can do? It's defined. Multiplication is defined. They're square matrices, so the product is defined, and we get a 3 by 3 matrix. And if you do that product, you should check and confirm this is what you get. Now, how does this matrix here compare to the original matrix A? Well, if you think about it, you'll notice that row 2 has been multiplied by 3. Okay? And so that's interesting, because how did we obtain E1? We multiplied row 2 of the identity matrix by 3. When we multiply this elementary matrix by A on the left, it has the same effect essentially on matrix A, just doing that. Well, look at E2. When I multiply E2 times A, look at what I get. Compare this to the original matrix A. What do you realize? Hey, rows 2 and 3 were swapped. And of course, and this was how matrix E2 was obtained from the identity matrix, by swapping rows 2 and 3. And then this one, E3 times A, if we're thinking the pattern is going to continue, we would think then what? This matrix must be what? Taking matrix A and doing what? Adding 2 times row 3 to row 1. Let's confirm that that's the case. 2 times 7 is 14, added to 1 is 15. 2 times 8 is 16, added to 2 is 18. And 2 times 9 is 18, added to 3 is indeed 21. So that is indeed the case. And so what we've illustrated here is an important fact. Multiplying a matrix A on the left, so it's real important we multiply on the left, by an elementary matrix essentially performs the corresponding elementary row operation on the matrix A. Okay? Now you might say, hey, we've been talking about Gaussian elimination or Gauss-Jordan elimination methods for solving systems of linear equations, and we have to do this row reduction, right? We have to do these row operations. You say, hey, now we don't have to do row operations. We can just multiply by the corresponding elementary matrix to do the transformation. Okay? Well, let me tell you, we don't want to do that. And here's the reason. If in terms of a lot of times we're thinking of that solving systems of linear equations and row reduction in terms of a program that we write for the computer, right? Because we're doing simple examples, 3 equations, 3 unknowns. But if you have 100 equations and 100 unknowns, you're not going to do that by hand. So the idea is we can just program the computer. But why don't we want to program the computer to do this matrix multiplication? Well, think about just this example here. How many operations does the computer have to perform to compute E1 times A? Well, remember how we do E1 times A. Each entry here is obtained what? By taking a row and dotting it with a column. So I have to do 1 times 1, 0 times 4, 0 times 7. That's 3 multiplications. And then I have to add, right, twice in that process. So that's 5 floating point operations, or five operations the computer has to do just to compute this one entry here. And it has to do that for every entry in the matrix. And there's 9 entries, 5 operations for each entry. That's 9 times 5. That's 45 operations we have to do. 45 operations. Whereas if I just use what we did with row reduction, just multiply row 2 of matrix A by 3, I will do 3 times 4, 3 times 5, 3 times 16, 3 multiplication, 3 operations. 3 operations versus 45. There's no doubt that the 3 operations is the way to go. And so this is not something we're going to do and use, but it is a convenient notation to thinking about the process of row reduction, and we will use it when we're talking about row reduction to write proofs and to come up actually with this algorithm we're going to see in just a minute. Before we move on, a couple other things about elementary matrices. They are invertible, and their inverses are elementary matrices. You say, well, how is that the case? Well, just think about how would we, think about when we multiply by a matrix on the left, it will do that corresponding row operation. So how would we undo the row operation here? How do we undo multiplying row 2 by 3? How would we get back to the identity matrix A? Well, we would multiply row 2 by what? The reciprocal, 1/3, right? So what does that elementary matrix look like? Multiply the identity matrix row 2 by 1/3. And there's the inverse matrix. Oops, sorry about that. Here's the inverse matrix, right, for the matrix E1. And you can see if I multiply this matrix times this one up here, I'm going to get the identity matrix. Well, what about the inverse for E2? How do I undo this? How do I undo swapping rows 2 and 3? How do I get back to the identity matrix? Well, interestingly enough, what do? I swap row 2s and 3 again, rows 2 and 3 again. I swap those. I'll be back to the identity matrix. So the inverse of E sub 2 is the same as E sub 2. Right, you swap rows 2 and 3 again to get back. And that's kind of interesting because when we talk about inverses, the analogy in real numbers are reciprocals, right? So if I have a reciprocal of a number, multiply them together, we get 1 for real numbers. But for matrices, when I multiply a matrix times its inverse, I get the identity matrix. But when we think about real numbers, and there's only one real number whose reciprocal is itself, right? The number 1. 1 times 1 is 1. But for matrices, like here's E2, its inverse is itself. And this is not the only matrix with that property. There's many matrices 3 by 3 that have that property. So that's something different again that we have with matrices. Okay, the last one's a little tricky. How do I undo adding 2 times row 3 to row 1? How do I undo that? Let you think for a minute. Undoing that operation is done by what? Subtracting 2 times row 3 from row 1. So what would the matrix look like if I subtracted 2 times row 3 from row 1, or added negative 2 times row 3 to row 1? Well, it would look like this. So if I took the identity matrix and added negative 2 times row 3 to row 1, this is what I would get. And here, when I multiply this matrix down here by E sub 3, I'll get the identity matrix. So basically all we're saying is that the inverses, they're invertible themselves, and their inverses, notice these are all in elementary matrices. So that's an important observation. Okay, I'm going to stop the video here as an introduction to elementary matrices. We're going to use these now in the next video to prove a very important theorem, and that theorem is a list of statements that are equivalent essentially to a matrix being invertible. And this will be really our big theorem that we'll work on and build throughout the semester. We will add many statements, and we will see the connections that this brings to the various areas we're going to be looking at later on. Very important. So we will work through the proof of this in the next lecture video. In the midst of that proof, we will find essentially the algorithm for finding the inverse of a matrix.